maybe tomorrow, we'll see. But for now, let's take a look at 21. What's it asking us? All right, so first thing to notice before we even look at the description, this is another one of these kind of recovery style ones where we just fill in the ... Okay, so that's going to make things tougher, but they're doing this to sort of guide us towards actually using bitwise operators as opposed to just writing out some long algorithm that's just going to do this by like converting to a string, converting to an array, all that kind of stuff. All right, so we'll take a look at our solution in just a sec, but first, let's see what it's asking us. So we're presented with an integer n. We want to find the zero-based position of the second rightmost zero bit in its binary representation. And it's guaranteed that one of those is going to exist, counting from left to right, from right to left. And we want to return the value of basically 2 to the power of whatever that position is that we discover. Okay, so that seems a little abstract, maybe a little weird at first, but let's take a look at the example and maybe that'll clarify some things for us. So we're given this number 37. And the idea is that they're saying we should return 8 in that case. Well, why 8? Well, basically, if we want to express 37 in binary, it's going to look like this, 100, 101. And if we take a look again at what it's asking us, we're looking for the second rightmost 0 bit. Okay, so if we're looking at these, there are 3 0 bits. We've got these two here, we've got this one over here. In some ways, I would say this is maybe not a perfect example because whether we're counting from right to left or from left to right, the second one is going to be this one. But I do want to clarify, it should be from right to left. That's the idea. So that's why it's this one over here. And basically we look at that and we say, well, okay, this is if we're looking for 2 to the power of that one, or of its position, and it's going to be a 0-based position, well, let's count from right to left. So with the first one here, it would be 2 to the power of 0, because this would be index 0. 2 to the power of 0 is 1. 2 to the power of 1 would be 2. 2 to the power of 2 would be 4. 2 to the power of 3, it would be 8. So that's why we're getting 8 over here. Okay, so that's basically the idea behind this. Now, how are we going to actually handle that? Could be a little tricky. We're guaranteed that there's always going to be a right answer here, but it might be something really like, it might have just been 100, right? Like if we're using, I guess that would be 4, I think. Yeah, 4. So if our input was 4, then basically the second, actually, let me write this down. So I'll try to sort of mimic the style of what we have here. Let me get a good, hey, by the way, just in case anyone's wondering, when I'm selecting a color here, there's a little like color window right up in here that I guess you guys can't see. It doesn't appear on stream, but if you're wondering like why my cursor's over here doing stuff, I'm selecting a color. So I wish you guys could see it. It's magical. You want to see the color I picked? It's this one. It's this green over here. Okay, great. Anyway, okay, so we've got, what was I saying? It was 4, right? So 4 in decimal is going to be the same as 100 in binary. So they're just using like the 10 here and the 2 here. Those are subscripts. They're using those just to represent what the base is. And in this case, this would be the second rightmost 0 bit. So basically what we would return here is just 2 to the power of, well, I guess this would be index 1. 2 to the power of 1, it'd be 2. So our answer here should be 2. Okay. So that's essentially what it's asking us. We'll talk about how we're going to solve that in just a sec. But before we do, our guy Rainbow Sprinkles has entered the chat. Yo, how are you doing? See that challenge I suggested? Yeah, I think so. It was the one that was, I forget what it was called, but it was like the first 5 letters, you want to make them all capital. The last 5 letters, you want to make them all lowercase. I think that was the one, right? You were saying it was a good example for regular expressions. Are we talking about the same one? I'll just close that for now. Because I did check that one out. Yeah, okay. I did check that one out. I agree with you. It's a good illustration of how regular expressions can really help us out. I mean, the thing is, like, it could take a while to do something like that without a regular expression. You might have like a big switch or something like that. I'm glad you mentioned regexp though, because that's actually what I want to use over here. So basically in all the previous bit challenges that we've looked at so far, I think we've pretty much, for all of them, we've started it the same way. At least for our first attempt, we've basically done something like n.toString with a 2 to make it a binary string. And then we've like converted it to an array by doing something like this with a little spread operator and array literal, or maybe like a dot split or something like that, or like an array dot from. But for this example, we're going to do something at least a little more efficient. I mean, the reason I would say I don't recommend doing this, the reason I usually start with this one and then find something better afterwards, is because it takes up extra memory that we don't need to, right? We've got n, we've got the number n. We sort of want to treat it as a number, because otherwise if we're converting to a string, converting to an array, it's just taking up a lot of extra memory. So here, at least, we're going to be able to save some memory by not converting to an array. So we're just going to keep it as a string. So why do I want to keep it as a string? Well, basically, like I was saying, we can use a regular expression on a string, right? So we've got a string like this. Basically, what we want to check for is we want the index of this thing, right? That's essentially it. We want to know where does this thing occur in our string, in our binary representation of the number. So basically, the idea is that, well, okay, what is this? It's a 0, and what comes after it? After this 0, we're going to have some number of 1s. Maybe it's like a whole bunch of them. Actually, hold on a second. Let me actually get a few numbers on screen here. So I'll just choose another color, and okay, I'll write this one out just, you know, so it doesn't feel left out or anything like that. And then let's get a few others. So we had 4, that was this one over here. That's what it looked like. What else could we use? Maybe something like, let's say 1 0 1 1 1 0. Yeah, something like that. And is that enough? That's probably enough for now. We'll grab another color. So I'm going to go back to my secret area over here. And okay, basically the idea here is that this was the 0 we're looking for. In this case, this is the 0. In this case, this is the 0 in this case. And we're going to take a look at these. We want to know, how can we use a regular expression to basically represent this whole end part of the string here? And if you think about it, yeah, we sort of have like, we've got this 0, and then we have some number of 1s. Maybe it's a single 1. Maybe it's no 1s. Maybe it's 3 1s. Maybe it's more. Maybe it's less. Anyway, the point is, we've got some number of 1s. Then we've got a 0, a single 0. And then we have some other number of 1s. Again, maybe it's 1, maybe it's none of them. I guess, you know, we could throw in an extra 1 on the end of this one if we really wanted to. Point is, it doesn't really matter. The main thing is that we're going to have a 0, and then 0 or more 1s, and then another 0, and then 0 or more 1s again after that. And then, importantly, the end of the string. Okay, so we'll use a regular expression to represent that. So we want to do, actually, hold on a sec. Let me just make some room here. I'll write out the regular expression that we want to use. So it's going to be a 0. It's going to be some number of 1. So I'll do 1 plus, and then a 0 again, and then another set of 1s, and then a money sign. Now, hold on a sec. I just want to explain this, make sure it's totally clear. You know, because we're saying that this is going to be the second rightmost 0, right? So then we've got this one over here. The reason I know there isn't going to be like more 0s here is because then if there were, this wouldn't be the second rightmost one. So we know there's going to be 1 0, maybe some 1s around it. How do I know these are all going to be 1s? Well, if it was anything other than a 1, it would be a 0. And the whole point is that we're trying to count specifically how many 0s we have. So, okay. The other thing is, remember, there could be no 1s in between these or after them. So technically the plus isn't the best. It should be the asterisk that we use here because we want 0 or more of these 1s. Or how do I put this? The number of 1s we want, geez, this is tough to say without using the word 0, which is what I'm trying to do right now. But basically we want no or more 1s. Geez, it sounds awkward. Some number of 1s, maybe none of them. Geez, I don't know how to say that. But anyway, I guess this is how to say it. That's the point. Okay, so that's going to be our regular expression. Basically, the money sign here represents the end of the string. There could be stuff before this. That's fine. This, we don't really care about that. The main thing is that we care about where it ends, because that's going to be the right end of the string. So what do we want to do with this? Well, basically, we want to do a dot match here. So we've got our string. We want to do a dot match with this regular expression that we just developed. And let's see what we get from that, just to get a sense of like what kind of stuff we're getting out of this. So when we do dot match, what are we getting? Okay, 0, 1, 0, 1. Cool. Nice. 0, 0. Good. 0, 0. Okay, so we're getting stuff that I guess seems to make sense here. I mean, we get a 0, some number of 1s, maybe none of them, another 0, again, some optional number of 1s there. All of these are sort of fitting that mold, that guideline over here. Some of them, well, actually most of them are just 0, 0. But something to notice before we go any further is that they're all inside of an array. Why are they all inside of an array? Well, because it's dot match. So dot match is going to look for, any matches of this that you have. And then it's going to return all of those in an array. So really, I mean, we know there's only going to be one match. We know that because we have the end of the string here. So we're going to go ahead and put a 0 there. It's the only element. I mean, we could also put something like, since we know we just want the 0th element in the array, and that's all we want out of this, we could get away, and yeah, there we go. So notice it doesn't have the array brackets around it anymore. It's just that one string. We could also say something like maybe a dot shift, I think would work, because that would take it from the left end of the array. In case there were more of them, this would guarantee that we get the 0th one. So yeah, same thing. I mean, it's not really going to make a difference. It's up to you. If you want to go with the @0, that's fine. If you want to go with the dot shift, that's fine. I'm actually going to switch it back to the @0. The reason is because doing it this way is just a lookup. It's not going to actually modify the array. And again, I don't want to modify an array if I don't have to. I don't know if it's going to make a big difference. I actually don't know which one of these is faster, but just intuitively, the way I kind of feel about it is that like looking up something in an array feels a little less invasive than actually modifying the array. So anyway, not that it's a big deal, but I just figured, yeah, anyway, in case you were wondering why I prefer this one. Okay, so yeah, we're getting this thing. Now, what are we actually trying to find? Well, basically the index of this, how far from the right this second 0 is. So in this case, I guess we'd say the index would be 1, 0, 1. Okay, if we look at this one, it would be 2, so 0, 1, 2. Okay, if we look at this first one, it'd be 3, 0, 1, 2, 3. We might be noticing a bit of a pattern here. It's basically just the length of this thing minus 1. So here the length was 4. We found the index of this 0 was 3. Over here the length was 2. We found the index of the one we were looking for was 1. So could we just do a dot length and subtract 1 from this thing? I wonder. Let's find out. Well, it's giving us the 3 here. So 2 to the power of 3 would be 8. Over here, 2 to the power of 1 would be 2. 2 to the power of 1 is 2. 2 to the power of 1 is 2. 2 to the power of 2 is 4. Folks, I think it's working. I think this is giving us what we want. One more thing that we'll need to do is basically raise 2 to the power of this exponent. Okay, so again, there are a couple ways we could do it. We could go with the old school method of saying math.pow and then making the first argument a 2, making the second argument this thing, and that passes the test. We could also make it sort of the more ES6 friendly way of doing it, which would be something like this, 2 to the power of this. So it's a little easier to read in terms of exponentiation. If we really wanted to make it very bitwise to sort of fit the theme of this module, we could do something like this: 1 shifted left this many times, because that's essentially what it is. I mean, if we shift it left 0 times, that's just 1. Shift it left 1 time, that's going to be 2. Shift it left 2 times, it's going to be 4, etc. This is basically another way of doing 2 to the power of whatever this thing is. And yeah, since this is the bitwise section, maybe we'll keep it that way. Another thing is, it's kind of weird the way these bitwise operators interact with the order of operations, like where they would fit into the whole bedmass thing or whatever acronym you used in school for that. But because of that, I think it's considered sort of like I don't know if you'd say higher precedence or lower precedence, but basically I think it will get executed after all the math operations, which means that this stuff, technically doesn't have to be in parentheses because it's kind of implied. At least that's what I think. Let's find out. We'll try executing that. Yeah, so we don't technically need the parentheses, so okay, we're probably fine like this. Let's just make sure it's passing the hidden test. We actually haven't tried that yet, so let's try submitting this. Submitted to the approval of the Midnight Society, and yeah, there we go. Now, this is the other thing. We only get 100 out of that. I mean, normally it's like 300 or something like that, right? So it feels like, I don't know, a little cheap, because I think their reasoning is like, we want to make it 100 because it's just a recovery. You're really just doing one line. But yeah, that's what makes it hard. You know, like, this would be an easier thing to do if we could do more than one line. So anyway, that's like adding insult to injury there. Expect that to happen again, by the way, when we get to the regular hell module. It's going to be hellish in some ways. Anyway, not right now. Thanks, though. Okay, so this was sort of our regular expressions way of doing this thing. But again, we don't want to use strings. We don't want to have to convert to a string. We want to be able to do this in a way that's just totally bitwise. That's what we're looking for, right? So let me put a 1 on that one, archive it, so to speak. And we'll get rid of this stuff because we're going to fill that in just a sec. Okay. Looks like Rainbow Sprinkles has a question here. So I cheated and Googled this. Can you help me understand what's going on here? Okay. Wow, that's looking pretty complicated. All right. We're going to go back to that one, okay? Let's work up to it. We're going to look at a different way of doing this, and then we're going to come back to that. So we will try to dissect that, but we'll develop our own bitwise way of doing it, and maybe we'll find that it's simpler, maybe more complicated. But yeah, thank you for asking, and we will go back to it. And Toching asked, do you have a Myers-Briggs type indicator? Yeah, that's a good question. I haven't taken the test in a while. I was like INFJ the first time I took it, I think, and then the next time it was like totally different. It was like ENTP or something like that. I'm not sure. I think if you go to 16personalities.com, it was called The Advocate the last time I took it. But like I said, it's been a while. Anyway, going back to this. The main point of this is that we're trying to keep this in, like, as a number. We don't want to convert it to a string, take up the extra memory if we don't have to, even though this is kind of cool. You know, we haven't had the opportunity to use a regular expression in any of these ones yet, so that's kind of neat. But really, this is the kind of stuff we want to be using, right? We want to be using our bitwise operators, our ands and ors, our nots, that kind of stuff. So, well, technically we did use one of them with this shift over here, but you know, that doesn't really count. So, okay, we want to be using these things. Now, I'm gonna move over to W3 Schools. Let me just scroll up a bit. They also have an article on this. I mean, we're looking at this and you might be thinking, well, that looks pretty similar to the Mozilla docs. I mean, is there really much point going into this? Well, yeah, I mean, there's a reason I wanted to look at this one because I want to talk about specifically this one. We've used not before, or at least I think we have. Maybe we haven't actually. Anyway, we're going to use it today. It's one that I definitely want to talk about. In terms of how we're going to use it, well, I actually want to take a look at sort of in depth how it actually works. So take a look at this. In this case over here, they have some examples, some results, some equivalents. We're looking at the number 5. Now 5 in binary, it would be 1, 0, 1. So here we're saying not 5, and the result we would get is 10. So that's weird. Now they're using examples here with 4-bit numbers, 4-bit binary numbers. We're saying they're 4 bits because there are 4 digits to them. Okay, so we're going to find that we actually in JavaScript use 32-bit binary numbers. Sorry, I'm just trying to avoid using the word bit too much. Anyway, so we use 32-bit numbers in JavaScript, so we're going to find it's actually different from this. We'll look at the specifics in just a minute, but for now, just to sort of simplify it, we're going to look at these 4-bit examples. So we've got the number 5. That can be expressed as 101 or, you know, technically 0101. We don't need the leading 0, but who cares? Anyway, the point is, if we put the not in front of that, then it's basically going to say, okay, well, not this would basically be the same exact number except where every bit is flipped. It's the exact opposite, so to speak, right? So instead of 0101, we have 1010. Okay, so we're saying it would be 10. The thing is, this is like 4-bit I think we call these unsigned binary numbers. Unsigned as in like positive or negative. They don't have a sign. They're just positive. We don't have negative numbers in here. If we wanted to have negative numbers in here, well, that's a little weirder. So we should probably talk about how we're going to handle negative numbers when we actually do use these 32-bit numbers. Okay. So we'll scroll down here, and what we find is it's coming up soon, I swear. Here we go. Okay, so this is basically how we handle negative numbers. We basically make the whole thing. Okay, this is kind of hard to handle, but it's kind of like we look at the whole thing in terms of like all ones instead of all zeros, and then we count up the way we normally would, but using zeros instead of ones. So normally, like the reason this looks a little weird, like we might think, okay, yeah, -5 is this, but isn't that kind of strange? Doesn't that look kind of more like -4, right? Because normally 5 would be 1, 0, 1. This is not 0, 1, 0, it's 0, 1, 1. So doesn't that seem a little strange? Well, the reason for that is because we would start, with our negative numbers, we would start with like, I'll just do the sort of 4-bit example over here. We would start with this. We would say this is -1. It's all ones over here. So that's our -1. Let me grab another color to represent that. So we would have -1. And then let's just count down from there. So -2, -3, -4, and we'll make it to -5. Yeah. So let's look at the binary representations. Well, just like the same way we would count up binary numbers for positive ones, we're going to do the same thing, but with the exact opposite bits. So we're going to say, you know, pretend these are like our zeros, and then the zeros are like our ones. I know it's kind of weird, but anyway. So we're counting up, so we're going to change this one to a 0. Then after that, we're going to say, oh, okay, so normally if this was like 0, 0, 0, 1, and we're counting up from there, we go from 1 to 2, and we get 1, 0. So instead here, we're going to have 0, 1. And then from there, we'll have 1, 1, 0, 0, like this. And then again, we want to get another 0 in here, but it's not like we really have room for it, so we have to shift this one to a 0, so we have 1, 0, 1, 1. And you'll notice that is sort of what we have right here. I sort of truncated it. I didn't include like these billion other ones over here. I guess it's actually 28 ones. But anyway, who's counting? Point is, that's why the -5 looks like this. So it's kind of weird. You know, we would expect it to look like more like a 0, 1, 0 if it really was just like switching all the bits. But I guess it shouldn't be surprised. We shouldn't be surprised that it's like this, because if we were to switch all the bits, well, that's what it means to be. I think it was here somewhere. Oh, maybe it's not. Well, that's what it means to be not 5. So did we have that? Was that? Yeah, here we go. So not 5 over here. Not 5 is where we switch every single one of the bits over here, and we find that what we get here is actually -6. So this not operator, it's kind of strange because the way it works, it technically just converts the number to, it multiplies it by -1 and then subtracts 1 from it. That's essentially what it's doing. Basically counting as 1 based, yeah, in the negative direction. That's the idea. Okay, so yeah, that's what our not operator is going to do. It's going to switch all the bits, but technically what it's also doing in terms of representing it as a number is it's multiplying the number by -1, it's switching the sign of the number, and it's subtracting 1 from it. That's the idea. Okay, so because of that, we have some interesting consequences. Like, for example, if we were to take the negative of the not, then we find something weird happens, because not 5 is the same as multiplying that number by -1, subtracting 1. If we do negative of that, it should basically just be the 5 plus 1, right? And it makes sense, because -6 would be +6. So another way, and let's go back over here. Another way we can say n plus 1, my claim, is to say negative not n, which is kind of strange. And yeah, it's not going to be the right answer, but yeah, look at that, 38, that's 37 plus 1. Here we have, okay, I'm not going to pronounce that number, but the 4 turned into a 5, so it's plus 1. Here, plus 1, again. I think probably it's convincing that these are all going to be plus 1, hopefully. Anyway, point is, that's something we can learn about not and how it all works. So that's kind of neat. I mean, it's sort of interesting stuff. We're going to look at some more quirks of this in just a sec, but I want to show you guys another page. So this is W3 Schools, really useful resource. I mean, I'm pretty sure it's in my recommended resources if you look downstairs. Or yeah, I didn't have room to write recommended resources, so I think it just says good resources if you're on my Twitch page. Anyway, the point is, where were we? Yeah, we want to look at some more of these kind of, tricks that we can do. I think Rainbow was in the chat a minute ago talking about some of these little hacks we can do, like that not x and x plus 1 sort of thing. So we want to talk about those. In fact, we've used some of those kinds of tricks already in some of these other challenges in the corner of zeros and ones. And it sort of got me curious. I was thinking, like, is there like a list of these things? Is there like a playbook for these bitwise operator hacks? And I didn't exactly find that, but I did a little Google search and I found this page. So I wasn't familiar with this, but this is catonmat.net. It looks like it's run by this guy over here, Peter Krumans. Hopefully I'm not mispronouncing that. Sorry if I am. Point is, I thought this was pretty cool. Low-level bit hacks you absolutely must know. And we start off with ones that we're pretty familiar with, so checking if an integer is even or odd. That's like a mod 2 thing. I think, I'm not sure if this was in the last one or before that. I think it was task 20. We looked at something like this, how x and 1 is the same as x mod 2. Oh, you have a book? What's it called? That'd be neat. Next one here, testing if the nth bit is set. So basically, shifting, we've looked at a number of these. In fact, a lot of these sort of have to do with that. If we start with a 1, we can shift it left n many times, right? So shift it once, now it's 1, 0. Shift it twice, now it's 1, 0, 0. Like we were saying before, this is basically multiplying by 2, starting with a 1, so it's like 2 to the power of this. And if we do the and here, we're basically just checking to see if that bit is set. Hacker's Delight, eh? That's what the book's called? Okay, I'm looking into that for sure. In fact, hold on a second, let me make a note of that. Okay, cool. Thanks, Rainbow. I'll look into that. Okay, so continuing with this. Basically, this is a way of checking to see if the nth bit is set. Now, when we say set, what we mean is it a 1? Okay, so just looking at an example over here, we've got the number 122, which can be expressed as this, 0, 1, 1, 1, 1, 0, 1, 0, 1, sorry, yeah. I think that was it. Anyway, point is, you can see the numbers right here. And then we're saying and 1 shifted 3 to the left. This is a way of asking, hey, is there a 1 in the position with index 3 here? And this is basically just going to either say yes or no in its own unique way. I mean, it's basically, its way of saying yes is going to be to return a 1 in the place of that bit. So basically it's not going to be 0 is the point, right? If we put the 1 over here, it doesn't matter. It's always going to be something not 0. If we get a 0 back from this, that means, no, it doesn't have the third bit set. It doesn't have a 1 in that position. But if we get a 1 back, well, yeah, the only way this could be a 1, since it's an and here, is if both of these things were a 1. And then again, since it has zeros in every other spot, it's basically just going to delete everything else, because even if it is a 1 originally, we're doing an and here, and if that's a 0, whole thing's 0. That deal's off. Okay, cool. So we'll continue with these. And basically we find a lot of them have to do with this sort of strategy of starting with a 1, shifting it left n many times. So we can check if the nth bit is set. We can actually manually set the nth bit. And that's kind of similar to one that we've done. Well, actually, it was pretty much exactly this, unset the nth bit. So the idea here is we're setting the nth bit because we're using an OR. So we're saying, okay, we've got this thing in here and we want to do an OR here. Now it's an OR, right? So basically anywhere where there's a 0, it's just going to keep it the same. Anywhere where there's a 1, it's going to make it a 1, no matter what it is. If it was a 0, it's going to be a 1. If it was a 1, it's going to continue being a 1. So I guess in both of these examples over here, they didn't start out as a 1, but basically if it started out as a 1, it's just going to be the same number. Okay, we look at this one, unset the nth bit. Well, we've seen this one. This is pretty much exactly the same as, I think it was task 17. It's like kill the kth bit or something like that. So that's basically exactly what we did for this one. So really similar to what we have up here, except instead of an or, it's an and instead of this number, it's not this number. So again, remember the way not works, it's gonna switch all the ones to zeros, all the zeros to ones. So we get something like this, and we wanna say and this, so that, keep in mind the way and works, if it's a 1 with an and, it's just going to keep whatever it was the same. So 1 and 1, it's going to be 1. 1 and 0, it's going to be 0. So it's just going to be the same as whatever we had originally in the other number. For the 0, when we do the and, it's just going to turn it to a 0. So basically, we just say, okay, if we want to delete, kill the 4th bit over here, then we're going to have this number over here with a 0 in the 4th, or in the place with index 4. When we do an and here, it's basically just going to zoom right in on this one and snipe it, just turn it into a 0. Okay, and then toggling the nth bit is basically where we use an XOR. So an XOR is kind of neat in the sense that if it started out as a 1, it's going to become a 0. If it started out as a 0, it's going to become a 1. That's basically just a quirk of the way XOR works. We've seen this before, right? So, I mean, it's only going to give us a 1 if exactly one of these things is a 1 and one of them is a 0. Okay. Going back to this is where things get a little more interesting. So we're talking about turning off the rightmost 1 bit. We can do that using x and x minus 1. So that's kind of interesting. These are more along the lines of the ones we want to start using. So the first 5 are, I think, fairly straightforward in the sense that we've used some stuff like that before. I don't want to say it's intuitive, but maybe more so than some of these other ones. If we want to turn off the rightmost 1 bit, well, we could go through the examples, we could go through how all these are working, but there are 2 in particular that we really want to look at today, and it's going to be the 7th one, and then we're going to jump to the 10th one after that. So isolating the rightmost 1 bit. So, okay, it's maybe not too clear why we want to do this yet, but we're going to find out. So their claim here is that it's x and not x. Well, that seems kind of weird. I mean, it seems surprising that that would isolate the rightmost 1 bit, but let's find out why that is. So basically, x and not x. Well, keep in mind, not x is basically where we're just gonna... okay, so it's not exactly the same as just flipping all the bits here. It's similar, it's very, very similar to that, but it's kind of like we switched all the bits and then we're adding 1 to it, right? Because a not would switch all the bits and then subtract 1. So it's kind of like we're doing a not and then adding 1. Yeah, that's one way to think about it anyway. So this is negative x over here, okay? It's kind of like, actually, maybe we should take a more detailed look at this. So we had our original number, it was 1, 0, 1, 1, 1, 1, 0, 0. Ooh, okay, sorry about that handwriting there, pretty awful. Okay, and then we want to convert that, so we want to do negative that, so I'll do it in 2 steps here. So first I'm going to say not this, and then I'm going to add 1 to it. So not this would be 0, 1, and a whole bunch of zeros over here, and then finishing up with 2 1s. And now we need to add 1 to this thing. So we'll add the 1, we'll do 0, 1, 0, 0, 0. Now when I try to add the 1, that's going to technically turn into a 2, so it's going to sort of bleed into the next one. Same thing's going to happen here, it's going to bleed into the next one, so we're going to have a 1 here, and then we're going to have 2 zeros to finish it off. And hey, that's what we've got here. Look at that, what a magical coincidence. Okay, so basically what happened is we started with our number, which we're calling x, then we did not x, sorry, kind of hard to do the tilde there, and then we did not x plus 1. Oh, that's barely even recognizable as letters. Okay, isn't that 2's complement? Wait, what do you mean 2's complement? Like 2's complement. When you say complement, you mean like the not? Because this, I feel like this would be a bit big to be 2's complement since it's got the other one over there. But maybe I'm misunderstanding the question. As for now, main thing, yeah, not x plus 1. Okay, well, not x plus 1. Okay, hold on a sec. Let's go back over here. So we found that negative not n was the same as n plus 1. Oh, that's 1 too many equals. Okay, so yeah, what do we have here? Another way of doing this, we could multiply everything by -1 here. So it would be negative n minus 1 over here. And so basically, if we want to rearrange this, we could just add 1 to both sides. So this would be +1, and we're left with just the negative n on the right side. So basically, this is all I'm saying, that negative n is the same as not n plus 1. That's sort of where that one was derived from. Does that make sense? Is that answering your question, though? I might be misunderstanding still. Okay, cool. So going back over here, all right, so we had this. This is not x plus 1, and what we just found is that that's the same as negative x. Okay, so basically we do this, and we do the and on this thing, and then what we find is, well, okay, here's the thing. We were saying we wanted to isolate the rightmost 1 bit, right? And we're doing that. We're getting that right here, the 1 right there. Yeah, we're getting it. It's what we're looking for, right? Or at least it's 2 to the power of whatever the index was. It's what we want. I mean, that's sort of the flavor of these kinds of questions, how they're phrased. But going back here, let's think about why. Why does that work? So basically, the first thing to notice, because we're looking for basically this right here, this 1 here. So if this is, in fact, the rightmost 1, then that means everything to the right of that has to be a 0. Okay, well, that also means that when we flip this, when we do the not x, everything to the right of the bit we're looking for is going to be a 1, right? So we're going to have 1, 1, 1. If there were more spaces to the right here, they would all be 1s. So we know when we do add the 1 to that, it's going to flip this, and turn that into a 1. So always we're going to have the 0s here where we had them originally. We're going to have a 1 here where it was originally. And we know that that's where it's going to stop. So everything to the left of that is going to be the exact opposite of what we started with, which means when we do the and, basically all of these are going to get nullified. They're going to sort of cross each other out is the idea. What a lot of math students would say is that they cancel each other out. Again, I don't usually like to use that kind of language, but that's basically what's going on here. So that's why that's going to isolate the rightmost bit. Now, there could be a whole bunch of 0s after it. It could be all the way to the right, and it's still going to work either way. I'm not sure if they look at the case where it's all 0s. Yeah, they do. And in that case, it would just be a 0 in that case. Okay. We've got another question. Why can't you do not n minus 1 is the same as n? Is that, what do we have? Not n minus 1 is the same as n. Well, would it be though? Because if we multiplied these both by -1, then we'd have something like this. So I think it would be negative not n minus 1. That would be equal to n. So hopefully that answers your question. At this point, we have an idea of how to isolate the rightmost 1 bit. We sort of have an understanding, hopefully, of how that's working. Now, like I was saying before, the next one we want to use is actually number 10. So we're skipping over a couple of them for now. We may revisit them. But for now, we're taking a look at number 10. We want to turn on the rightmost 0 bit. That might seem a little strange too, but trust me, it's going to be relevant to the problem we're about to look at. So turning on the rightmost 0 bit, the claim here is that we have x or x plus 1. Okay, so let's take a look at how this is working. First of all, we take the original, didn't quite get it, and we take the original here, and then we just add 1 to it. Okay, so we just put a 1 there, and then basically we just do an OR. So the OR is not really going to change things very much except for that last one. So it's just taking that 0 we had over here, turning it into a 1. Okay, now we've got this one over here, and we find that it doesn't have a 0 until the bit with index 3. So when we add 1 to this one, it's going to turn the rightmost 1 to a 0, second rightmost 1 to a 0, the third rightmost 1 to a 0, and it's going to turn this one into a 1. So when we do the OR on this thing, well, basically all of these ones remain 1s because, you know, it's an OR. These 0s aren't going to mute them or anything like that. Whereas since we have a 1 here now, it's basically going to fill in that 0 over there. Okay, so that's basically the idea behind this. In this case, we've got a 0 right over here. It happens to be, you know, technically not part of the number in the sense that it's a leading 0. But again, the same thing is going to work. We add 1 to it, we do the OR, now it gets filled in. Now we have a 1 there. In this case over here, it's all zeros. So this 0, it's going to basically turn into a 1. Now it's a 1. Not too surprising. That one's a lot like the first one over here. If we have all zeros, we're going to get a single 1 appearing over here. If it's all 1s, it's going to continue to be all 1s because there's no rightmost 0 bit. So that's basically the idea there. Okay, so if we want to turn on the rightmost 0 bit, we're going to do x or x plus 1. Okay, and of course, there are other ways we could look at that. We could say x plus 1 is the same as negative, not x. But, you know, I don't think we really need to look at it that way. I think we're good for now. So what did we learn? Let's go over here. Let's try to summarize some of our knowledge over here. So let's put in a little text field somewhere. So we'll say fill in the rightmost 0 bit. Okay, that's what we want to do. How do we fill in the rightmost 0 bit? Well, that's where we did something like n or n plus 1. And again, I technically don't need the parentheses on this, but it's a good thing to include. It's just more clear to the reader that way. Okay, so that's one thing that we found. And then we also found that we could isolate the rightmost 1 bit. Okay, so 0 bit, 1 bit. We could say set or unset as well. It's up to you. I mean, we're basically talking about the same thing. Okay, so we want to isolate the rightmost 1 bit. How do we do that one? I think it was n and not n, negative n. That's what it was, right? N and negative n. Let's just check. Did I get this one right, first of all? X or x plus 1. So I think I said n or n plus 1. Yeah, okay. And we'll go back up to 7 and yeah, x and not x. So n and not n. Great. So these are the tricks that we're going to use here. And we basically want to use these tricks to try to develop some way of answering this question here. Now, what was this question here? Maybe we'll use the example. So 37 was 100, 101. What we wanted was the second rightmost 0 bit. So we want to know this one, and specifically we want to know 2 to the power of that one. So like basically what we want is like a 1000. We want that number if we can get it. So 100101. Okay, let me write that down as our example. So switch back to pen and we'll say n is going to be assigned the value of 100101. Okay, so here's what I want to do with this one. Basically, this is the game plan, okay? I want to fill in this 0 here, okay? If we fill in this 0, then we'll just have all 1s after the one we're looking for. And maybe we should like highlight that one we're looking for. This is the one we're looking for, okay? So the answer that we want to get is going to be this, okay? 1000. That's the answer we want. And these are all in binary right now. If we wanted them in decimal, this would be 37, this would be 8. Okay, so what are we going to do with this? Well, basically the idea is that like I said, we're going to fill in this 0. Okay, so we're going to use this trick over here to fill in the 0 over here. Once that's a 0, once this is a 1 and no longer a 0, we're going to sort of use this trick, but not exactly. We're going to do it a little bit differently. So let's first fill in the rightmost 0 bit. So we start with n and then we do n plus 1. So n is going to be 100101. We can see it, it's right above us. And then n plus 1, well, what would happen? Basically, 1 and 1 is going to make, well, 1, 0, right? So instead of this, we're going to have 1, 0, 0, 1, 1, 0. Okay, that's the idea. And we want to perform an OR operation on this. So I'm just going to switch colors for that just so that it doesn't look like a 1. Maybe it still looks like a 1. I don't know. Anyway, the point is, that's the operation we want to do. We're going to do an OR. So 1 or 0, yeah, 1. 0 or 1, yeah, 1. 1 or 1, well, definitely 1. 0 or 0, we don't have a 1 in there, so that's a 0. Same with this one over here. And 1 and 1, yeah, it's 1. That's right, 1 or 1 is 1. Okay, great. So, well, great. This did what we wanted. It filled in the 0 bit over here. So, great. That's what we want, right? Okay. So, okay, maybe it's not exactly what we want because we're looking for this thing over here. But take a look. This is basically 1 followed by 3 zeros. Here, if we look at the same last 4 bits, we've got a 0 followed by 3 1s. So it's the exact opposite of this. So could we just use like a not this? What would that look like? So I want to write that down somewhere. Maybe I'll just get a bit extra space. And we'll say not n or n plus 1. Okay, that's what we're looking at. That's what we're going to get from this after we do this thing over here. I'll just switch colors again. It's going to be 0, 1, 1, 0, 0, 0. Great. Yeah, not this, it's that. Okay, so it's equal to this thing over here. 0, 1, 1, 0, 0, 0. Well, take a look. We've got part of what we're looking for here. We've got the 1, 0, 0, 0. It's just that we've got some other junk over here to the left of that. But hey, am I hearing that we want to isolate the rightmost 1 bit? Because we have a way to do that. So take a look. This number that we get here, what we want to do with that is AND that with its negative self. Okay, so we're going to AND that with its negative self. And let's see what happens when we do that. So let's switch colors again. Get back the pen. Okay, so we've got this thing over here, which is 0, 1, 1, 0, 0, 0. And we want to AND that. I'll write in the operation in just a sec. But what is its negative self going to look like again? Well, basically, remember, the negative self is the same as doing, do we have it written here still? Not quite. Maybe we can go a few steps back to where we had it. Negative. Wait, did we have that there? I'm not sure. Oh, yeah, I went back too many times. So we had the negative. Yeah, that's it. So the negative n was the same as not n plus 1. So that's what we want to do over here. So not n, well, that would be, I might as well write it in. So it would be 1, 0, 0, 1, 1, 1. We want to add 1 to that. So we would say 1, 0, 1, 0, 0, 0, right? Because all of these sort of get displaced. This would represent 7. We add 1 to that. This part would represent 8. Okay, so that's what we have, 1, 0, 1, 0, 0, 0. Let me just do 1,000 undos, and I'll get that same number in there. I hope we remember it. It was 1, 0, 1, 0, 0, 0. So this is negative this thing, okay? And we want to do an AND, I believe, with this. So 0 and 0, yeah, that's a 0. 0 and 0, still a 0. 0 and 0, definitely a 0. 1 and 1, oh, that's a 1. 1 and 0, that's a 0. And 0 and 1, that's also a 0. So what are we getting from this? Well, we're getting 1, 0, 0, 0. Folks, that's 8. It's what we're looking for. So, cool, we got it. So all we need to do is basically get this number over here, so not n or n plus 1, and then we need to AND that result with negative itself. Okay, that's the game plan. So we only have one line here, so we're gonna have to sort of cram that in, but let's start with this. So we have not n or n plus 1. I think that was it, right? That's what we were looking for. It's not what we're actually looking for, but I think it was sort of the piece of the puzzle, right? So not n or n plus 1. So that's giving us something, I mean, yeah, basically the result we're getting here, it would be negative 40 in this case. You might look at that and think, well, that doesn't look like negative 40. That looks like 24 or something like that. The thing is, we're only showing part of the number here. Technically, there would be like 1,000 other ones to the left of this, which is what makes it a negative number, like we saw earlier with that W3 school stuff, right? Basically, if we have something negative, it's going to have all ones. Okay, so basically, going back to this, that's part of what we're looking for. It's this thing. What do we want to do with this thing? Well, we want to do AND negative this thing. Okay, so let's try that. So we'll say AND negative yourself, right? There's all of this. So let's try that. Paste that in and we'll run it. And what we'll find is that it passes the test. Beautiful. Look at that. This is great. We're not taking up any extra memory. We're not converting to a string. We don't need to run a regexp match on this. It's just bitwise operators, and it gets the job done. Well, does it really get the job done? Let's find out. Is it passing the hiddens? Hopefully it is. It is. Okay, cool. Well, that feels good. That's pretty nice. We like that, I think. I like that. Hope you like that. It's looking a little messy, so I want to just clean it up a bit. Now, again, I do like the idea of... oh, see you later, Rainbow. Thanks for stopping by, man. Okay, so I like the idea of this, of putting these in parentheses just for clarity, you know, just to make it clear that, like, we would add the one first and then we would do the or. Technically, we don't need these, though. We could just get rid of them if we wanted to make it look a little more succinct. We'll run this, and yeah, there we go. Okay, so that works. Now, another thing that we could do is, we've got negative, not this. Well, we saw this earlier. That's the same as just doing that thing plus 1, right? So we could just put a big old 1 on the end of that. That's another way we could represent this thing. It's up to you. It's going to work either way, so whichever. Yeah, your call. I think at this point, let's see. I'm going to keep it, I don't know. Should I keep it like this? Should I keep it the other way? Any suggestions? I don't know. I'll do it like this for now, just to make it super bitwise, I guess. Just to make it maybe a little more clear how it's sort of connected to these two rules that we found earlier. I don't know. If you prefer another method, that's totally fine. Speaking of which, I am going to instantiate another one of these. I'm going to throw a 2 on the end of this. Because there's sort of another way we could look at this. Well, I mean, okay, not totally another way, but I just want to point out, like, this whole thing, it's kind of unruly. It's kind of big, right? And then we've got that whole thing again over there. So another way we could do this is sort of assign a variable inline. I don't know if there's a particular name for this kind of strategy, but we've got x is assigned the value of this thing, which was like, you know, the negative 40 the first time around. And then we could say, well, all of that was just x, right? So we could do something like this. And will that work? Yeah, it works. No problem. Well, kind of a problem though, I think, because notice how the X is in green. It's, we didn't put like a var or a let or a const or anything like that in front of it. That's kind of not good. And even if we tried to, I don't think it would like us very much. Yeah, it doesn't like that. So we can't really do an inline like var sort of thing. So it's making things a little bit complicated, right? I don't like the idea of like declaring a variable without, well, formally declaring it, I guess, you know? I think this is kind of sloppy. I'm not a huge fan of it. So I want to do something like this, but it's not going to be exactly this. So we're going to back up a bit. And instead of assigning a new variable, basically, well, take a look. We're taking this n thing here, right? What are we doing with that n thing? Well, we're saying we want to take n, or we're going to use a bitwise or on it with n plus 1. And then we're doing the same exact thing here. Well, why bother doing it twice? Why not just say, store that value of n and use that for the next time? So we'll say, you know how we sometimes do like n plus equals 1 or like, you know, times equals -1 or something like that, right? We're used to those kinds of things with other operations, but we can actually do that with this bitwise operators as well. So we can say n or equals n plus 1. And then since we've already done the or equals part, my claim is that we won't need to do it over here. So we can just do something like this. Hey, not bad. Okay, so then at this point, I think this is probably maybe a little more clear to just do a +1 like that. You know, something like this. I mean, now we're kind of repeating ourselves in a new way because we have the n plus 1 over here. So, geez, I don't know. We could store that as a variable, but I think this is probably good enough. I think it's looking nice and succinct. It's pretty slick, if you ask me. I think it's pretty slick. Let's just make sure it passes all the hiddens. Let's try running that. We'll control enter, and yeah, it does. Okay, so we're passing the tests. I guess none of these looked all that unruly. Like even this one that was kind of, you know, iffy. Even that didn't look too bad compared to some of these previous ones. I mean, yeah, we definitely could have looked at this in another way. We could have looked at it using like a reduce and all that kind of stuff, and it could get complicated, trust me on that one. I didn't really want to get into that too much, but you know, it's funny. I look back at like the first time I had done this one, like my first attempt at this on the Zero Cool account way back in the day when the arcade was new and fresh. And geez, I did some stuff there. Like, it was very, very hacky, and like, yeah, I won't repeat it, but the point is, it was not nice looking stuff.